diagram maps out 50 essential algorithms. So far, we've looked at ways to sort data, search it, and verify it using cryptographic hashes. Now, at algorithm 48, we enter the realm of secret messaging. This is the Advanced Encryption Standard, or AES. It is the symmetric block cipher protecting nearly all digital communication sent today. But we didn't always have it. In the late 1990s, the previous US standard, known as DES, faced a crisis. Its 56-bit key was simply too short to withstand modern computing power. In 1998, a custom-built machine cracked a DES encryption message in a matter of days. A replacement was desperately needed. But rather than designing a new cipher in a classified government basement, the US made an unusual decision. They asked the public to build it. The National Institute of Standards and Technology issued a global challenge. 15 cryptographic algorithms were submitted by teams from around the world. These candidates were published openly, inviting anyone to tear them apart. One design stood out. Created by two Belgian cryptographers, Vincent Reidman and Joon Daemen, the Rijndel cipher beat out submissions from tech giants. It won because it struck an optimal balance of intense security, fast software speeds, and hardware simplicity. In November 2001, NIST formally published Rijndel as FIPS 197, officially designating it as the Advanced Encryption Standard. Because its math was published for anyone to scrutinize, and because it survived years of relentless attacks without failing, it earned immense trust. True digital security relies on verifiable mathematics rather than hiding how the code works. AES is a symmetric cipher. That means the exact same secret key is used both to lock the plaintext into ciphertext and to unlock that ciphertext back into plaintext. This flowchart outlines the architecture. AES processes 128-bit blocks in a 4x4 state grid. Subbytes swaps bytes for nonlinear confusion. Shift rows and mix columns scramble the grid, causing diffusion. Finally, add round key mixes in the secret key. Repeating this loop turns data into irreversible noise. This chart shows exactly how diffusion works during the shift row step. It applies a mechanical rotation to the grid. Row 0 stays put. Row 1 shifts left by 1 byte. Row 2 shifts left by 2, and row 3 shifts left by 3. This physical spreading creates what cryptographers call the avalanche effect. If you flip just one single bit in the original input, that tiny change cascades through the shifting grid until every single output bit is altered. By combining the nonlinear confusion of byte swapping with the rapid diffusion of matrix shifting, AES protects against linear and differential cryptanalysis. This chart compares standard AES key sizes. The algorithm requires constant work per block, making it incredibly fast. The 256-bit key space offers 2 to the power of 256 combinations. Brute forcing that number would take longer than the age of the universe. In practice, the cipher is easy to deploy. Using a Python library like Fernet, you simply generate a key, use it to encrypt your text, and then use that exact same key to decrypt it. The security of the message depends entirely on the protection of the secret. While the math is impenetrable, any compromise of the shared key immediately voids the encryption. AES secures your HTTPS web sessions, encrypts your hard drives via BitLocker, protects WPA3 Wi-Fi networks, and tunnels your VPN traffic. Thanks to hardware acceleration, modern processors execute it at gigabytes per second. But the cipher does have strict limitations. It guarantees confidentiality, meaning no one can read the message. It does not guarantee the message hasn't been tampered with, unless paired with an authentication mechanism. Despite its strength, AES faces a significant logistical requirement. It only functions if the sender and receiver have shared the secret key over a secure channel before communicating on a hostile internet. This algorithm is detailed in Chapter 14 of 50 Algorithms Every Programmer Should Know by Emran Ahmed. To solve the key sharing requirement, we have to find a way for two strangers to establish a shared secret in plain sight. And for that, we need Algorithm 49, RSA.